Hi everyone, this is Avital Breverman with the Hydrologic Engineering Center. This video is a recording of the Modeling Baseflow lecture that was delivered as part of the Hydrologic Modeling with HEC-HMS PROSPECT course in November of 2024. The objectives of this lecture are to describe how interflow and baseflow are simulated in HMS, provide an overview of the available baseflow methods within HMS, and discuss the applicability of baseflow methods within HMS.
All right, so let's first define baseflow. When you're doing event-based simulation, the majority of that event, that hydrograph, is typically caused by direct runoff. This constitutes the flood magnitude in most cases, not all. But we also have this other component, baseflow, which is really important for overall runoff volume and duration. The amount that baseflow contributes to the hydrograph really varies based on the climatological regime, the event time of year. Baseflow in general as a concept includes interflow and then baseflow or really saturated groundwater flow. And so it's comprised of runoff that infiltrates into the ground, flows down gradient, and then flows back into the land surface in small channels, streams, and rivers. Baseflow in HMS, so that basin model method, is comprised of both interflow and then saturated groundwater flow. Some methods only simulate that in a lumped way, kind of a combined way, I should say. There's one method, linear reservoir, which we'll talk about, that allows you to actually separately model interflow and then saturated groundwater flow. And what we're showing here in red, right, so interflow is this kind of quicker responding portion, and then baseflow is the slower responding portion that tends to exist between rainfall events even during dry periods. All right, so there are two kind of paradigms or approaches to modeling baseflow. There's process-based and then there's conceptual. In HMS, we currently only have conceptual baseflow methods. So in the same way that we don't use full momentum equations in HMS to route flow in reaches, right? We don't have process-based, we don't have a full groundwater model in HMS, at least not currently. But we can do a pretty good job approximating and simulating baseflow using these conceptual models. There's a lot of different methods out there for baseflow separation, different techniques. We don't really do that in HMS, but there are just kind of a couple ways that you should know about. So one is using the point of inflection on the receding limb of this hydrograph. So by point of inflection, I mean that the hydrograph changes from concave down typically to concave up, right? You can see that kind of break between the red line and then the black line above it. Another way you can eyeball this is by plotting your hydrograph in log 10 space. If you do sediment hydraulics, everything is plotted in log 10 space. We don't often do that, at least in hydrology, but that can help you identify visually different parts of the hydrograph and separate out baseflow from direct runoff portions. All right, so let's talk about interflow and baseflow separately. Interflow is quicker responding than saturated groundwater flow, but it's slower responding than direct runoff, right? So that's the distinction. It is flow through the unsaturated zone, so beneath the ground surface, but above our groundwater table. And like I said, the response time is longer than surface runoff, but slower than saturated groundwater flow. All right, then baseflow or groundwater flow is infiltrated water that percolates into the groundwater layer and that contributes to streams when the flow is high enough, right? So much slower responding and can persist between rainfall events. All right, so let's talk about how you actually parameterize or select baseflow methods in HMS. You can select the method either by selecting first a subbasin element and then using the component editor. So shown here, I'm showing the baseflow method drop-down menu. Or you can change the method that you're using globally, meaning for all subbasins, by using the Global Change Methods tool from the parameter menu. Once you actually want to parameterize your subbasins, you can either do that in the component editor, so subbasin by subbasin, or like we've talked about, the global editors. And hopefully you're seeing here, I have 5, or I guess 6, you could say, baseflow methods: none, bounded recession, constant monthly, linear reservoir, nonlinear Boussinesque, and recession. So we'll talk about 2 of those in this lecture. Like I said before, because all baseflow methods in HMS are conceptual, calibration is really, really, really important. like I said, 5 baseflow methods. Constant monthly is super simple. It's not that commonly used because it's kind of an oversimplification. We will talk about recession and linear reservoir methods in this class. These are the most widely used, at least within the core. And the linear reservoir method is the only baseflow method in HMS that conserves volume, and we'll talk more about that. Just a reminder, we have a technical reference manual, and for a lot of these computational methods, we have a page for applicability and limitations, so kind of the pro and cons, or where some of these methods are applicable and where they are oversimplifications and should be avoided. All right, so in order to visualize results from Baseflow, you have to look at your sub-basin elements, right? Because Baseflow is a land surface process, so it lives in these sub-basin elements. It's not associated with junctions or reaches. And so you can access the time series from the Watershed Explorer's Results tab. You can create plots and summary tables from the sub-basin elements only. When you're working with volumes, a lot of times these summary tables are super useful because they give you things like loss volume, baseflow volume, total volume, right, as expressed as a depth. So again, when you compute results, you can view the baseflow results by selecting a sub-basin element. Here I'm showing components involved in the linear reservoir baseflow method, and we'll talk a lot about that. This is super cool because you can actually visualize the contributions from multiple layers. So you can actually parameterize your baseflow using multiple linear reservoirs, and I will define that. So for example, here I'm plotting total outflow in blue. My total baseflow is in red. Those are both solid lines. And then I can separately plot baseflow layer 1, which is in like a dashed magenta color, and then baseflow layer 2 in this dashed light green color, right? So I can actually visualize separately contributions from 2 baseflow layers, and this is typically parameterized such that they represent interflow and then saturated groundwater flow, right? So that's pretty cool. I think David Ho actually implemented this in HMS. It's really cool. It's useful when you're calibrating. All right, we're going to talk about recession baseflow method first, and then linear reservoir. So recession baseflow is pretty simple, and it is mainly used for event modeling. So short-term simulations, not continuous simulations. And the way we model baseflow is using basically an exponential decay function. This is your recession equation here. It's Q sub t, so the flow at time t is equal to Q naught times our exponential decay constant k raised to the power of t. So when you're at time 0, t equal to 0, what is Q sub t equal to? Q naught, right? Yeah, this becomes k to the 0, which just means k sub t is equal to the initial flow, right? Which makes sense. We're modeling this recession part, right? It is the receding hydrograph, and we'll talk about how HMS knows when to initiate baseflow, and then kind of how this shape looks. All right, so here are your parameters for recession baseflow. Not too many. You have an initial discharge, which you can specify either as a rate per area or a rate, and we'll talk about that. A recession constant, that was the K on the previous slide, and then a threshold for basically initiating baseflow, or when the model differentiates between direct runoff and baseflow. And this can be specified either as a flow rate or a flow threshold, or a ratio to peak, which is what I'm showing here, right? So you have a drop-down menu for the threshold type, and then this lower field changes depending on the threshold type selection. So we'll talk through all of these parameters in more detail. Let's just look at the sensitivity of our hydrograph to the recession constant. I like these plots a lot. I think it helps when you're newer to these parameters. So a recession constant closer to 1, so this is 0.9, means that you have a flatter recession curve, right? It also means that you have more volume in your receding hydrograph, right? So that's important. If you think back to that equation, Q sub t equals Q sub naught times K to the T. So if your K is higher, right, it means that Q sub T is going to be closer and closer to your initial flow, regardless of what time, right? It maintains a higher flow rate. As I decrease my recession constant, I get a steeper drop-off, a steeper recession curve, and less volume, right? So that's important, and we'll talk about that and how it relates to hypothetical storm modeling. The downside of the recession method, the recession baseflow method, is that it models all of your baseflow with a single recession constant, right? So it doesn't differentiate between baseflow and interflow, or what I should say is groundwater flow and interflow, right? So it's pretty simple. typically only applicable for event-based modeling. Okay, so now we're going to talk about how HMS knows when to switch between direct runoff and baseflow, and that is selected based on the threshold type. Like I said before, you have two options: ratio to peak or threshold discharge. A threshold discharge just means that you're saying when my flow gets below a specific value, so an absolute value, let's say 100 CFS, that's when it switches from direct runoff to baseflow. It's not really flexible, right, because your peak is going to vary, and so that threshold that discriminates between direct runoff and baseflow should also vary. And so we typically recommend that you use this ratio to peak. This is expressed as a decimal, right? So 0.5, 0.9, whatever. And it's easier to apply broadly across basins. It's also generally consistent across sub-basins in a watershed, right? So it's a lot easier to extend that parameterization. So just so you know, if I have a recession constant of 0.5, let's call my peak 7,000 CFS. That means that I switch from direct runoff to baseflow at 3,500 CFS, right? I just take 0.5 times my peak magnitude of 7,000, and at 35 CFS, which you can actually see this is about 3,500, this now becomes a baseflow curve. Higher ratio to peak means that that switch happens at a higher magnitude flow, and a lower ratio to peak, so 0.1 here, means that I have to get to 10% of my peak flow magnitude in order for that to become baseflow. And again, here, notice that this doesn't really impact the peak, or it doesn't impact the peak at all, but it does impact the rate of baseflow and then the volume in the system, and we'll talk about that a little bit more at the end. All right, and then finally, you have to specify the initial discharge type. You have two methods again: discharge per area or discharge. Discharge, again, is just an absolute value. So my initial flow rate is 100 CFS, right? That's going to change depending on when your simulation starts, as well as the upstream drainage area. And so we recommend that you actually use discharge per area because, again, it's easier to apply broadly across subbasins in your watershed. And the way that you compute this is hopefully you have an observed hydrograph that you're using to get started. You look at the flow at the start of your simulation. So in this case, it's about 1,500 CFS. And then you divide that by the drainage area of your subbasin, right? It's a super easy computation. It's important to select this starting point with some thought involved, right? If you're doing event-based modeling, you don't want to spend a lot of time on the initial discharge, like spending time parameterizing that. And so it's usually useful to select the start of your simulation to correspond when you have only groundwater baseflow, right? So you don't want to actually start your simulation when you're like coming off the tail of a previous event, because then you have to capture the receding limb of another event's hydrograph, right? So typically I would start this during a dry period between rainfall events, where all I have to do is say, okay, my initial discharge is 100 CFS maybe, and my upstream area is 100 square miles, so 100 divided by 100 means I can use 1 CFS per mile squared as my discharge per area requirement. And again, like ratio to peak, discharge per area is easier to apply broadly across watersheds. And here I'm just showing initial discharge of 10 CFS, 5 CFS, or this is probably CFS per mile squared. And if I had an observed hydrograph, I would be looking to make sure that that simulated initial portion of the hydrograph matches well with the observed. Recession baseflow can be used for continuous simulation. We strongly recommend against it, and I'll show you an example why. This is my HEC graph here showing my losses as well as total precip. And then on the lower panel here, I have observed hydrograph in black. So I have a little double peak. I have my total simulated flow in blue. And then the purple dashed lines show the computed baseflow. So I actually have two events here, right? This one's probably more of my concern than the second one, but I get a single recession constant using this recession baseflow. So what I'm seeing here is that for the first curve, I'm generally matching the recession of the hydrograph pretty well, right? But the second curve, it's too steep of a drop. And there's really nothing I can do about this recession without changing the fit of my model here, because again, you get one recession constant, right? So it's not always the best when you have multiple peaks or you're looking at longer term periods. And again, it simulates interflow and saturated groundwater flow in a combined way. So I mentioned a handful of slides ago that linear reservoir baseflow is the only baseflow method in HMS that conserves volume. That means when you use recession baseflow, you can actually introduce volume into your system, right? So you might end up with a total computed volume from your hydrograph that exceeds the precipitation volume. Right? We're not actually creating volume in real life, but that is a function of the recession baseflow method, and that's really important to compare. So here I have a precipitation volume of 32.76 inches. My total discharge volume simulated is 33.14. So that's a roughly 0.4 inch difference. In some cases, that's not a huge concern, right? That's not actually a huge difference. But as you use this over longer and longer term simulations, that can add up a lot and that needs to be evaluated, and that's often why recession is not the best method for continuous simulation, right? Some of that comparison is going to depend on the event magnitude, right? 0.4 inches off of like 32.8 inches isn't drastic, but if that magnitude was lower, I probably would be more concerned. I said we're going to talk about hypothetical events. So hypothetical events are typically, we're looking at rare probabilities, which means that the volume in our system is very, very large, right? And I talked about if you have a high ratio to peak, that receding limb of the hydrograph is not steep, right? It's a kind of a slow drop off, which means that you generate a lot of volume in the receding limb of the hydrograph. This can mean that you're creating a lot of volume during those hypothetical events, right? Because if your peak is high and it's a slow recession, you're introducing a lot of volume into the system. It might mean that you are simulating way more volume than the precipitation input, right? So that's why it's really important to check when you're working with hypothetical events, right? So you typically want to reduce the ratio to peak and then also compare computed and observed volume. Okay, that was it for recession baseflow. The ratio to peak tends to be consistent across a watershed, right? And some of that depends on like how large your watershed is, right? Especially in the sizes that we work in the core. So that is why we recommend using ratio to peak. If you use a threshold discharge, right, a really small subbasin is going to have a peak that's much less than a larger subbasin typically, right? And so that threshold value could be 100 CFS in one basin and 10,000 in another. Hopefully not, because your subbasin should be relatively uniform in size, but this ratio to peak is much more consistent, and it doesn't rely on drainage area. So yeah, and within watersheds, right, like some areas might have a ratio to peak that's closer to like 0 or closer to 0.1, whereas some have the ratio to peaks that are closer to 1. So that does vary by location, yes. So that's absolutely true. The question was related to whether using threshold discharge to differentiate between the direct runoff and baseflow is less applicable across multiple events than ratio to peak. And the answer is yes, right? Because if I had a threshold discharge of 2,000 CFS, then in this first, or I really should say 1,000, right? Because this peak is like 1,500 or 1,600. So let's say my threshold discharge was 1,000. That means that this hydrograph is all direct runoff until it hits 1,000 CFS, right? That's most of the peak, right? Whereas in this one, that's barely any of the peak. And so using a ratio to peak is much more applicable here, but the ratio to peak can vary within a subbasin between events, right? You're seeing that right here, is that whatever ratio to peak value I'm using for the first event fits pretty well, but it's not such a great fit in the second one that typically relates to event magnitude. So linear reservoir, this is kind of using the phrase in the definition, but the linear reservoir baseflow method uses this concept of linear reservoirs, which I'll define, to model the movement of infiltrated water. One of the major advantages is that it can be used to model interflow, right? So this yellow portion, this quicker responding flow, and then saturated groundwater flow, this slower responding, you can explicitly model those separately, which is really useful in a lot of areas that we work in. It's also really useful and important for continuous simulation. Let's talk about what a linear reservoir is. All it does is it relates there's a linear relationship between storage and discharge, right? So the storage at some time t is related to the outflow at that same time by this linear reservoir coefficient, R. We'll talk more about that. And then we also use the continuity equation, which just says the change in storage is equal to the inflow minus outflow. Okay, so hopefully you've at least heard of continuity, but this is what creates a linear reservoir. All right, so linear reservoir is great because it's designed to work with all loss methods, and you've seen this diagram before today in the loss model or loss methods workshop. All losses in the initial and constant, curve number, and green amp loss methods are available to the Baseflow method, right? That water enters the Baseflow layer. Only the constant loss rate losses, which represent saturated conditions, right? So when you're using deficit and constant, when the soil layer is not saturated, all precip enters that soil layer, right? Until that soil layer is saturated, none of that loss is available to the Baseflow method. Once it's saturated, it infiltrates through at the constant loss rate, and then those losses are available to the Baseflow method. And then we'll talk about how you can parameterize linear reservoir Baseflow to have up to 3 linear reservoirs, or I should say 3 layers. Yeah. So linear reservoir can have 1, 2, or 3 reservoir layers. You have this like toggle combo box here right up top. I think we currently have 2, but you can have up to 3. You could use 1, right? So this linear reservoir can be used in continuous and event-based simulation. If you're doing an event-based simulation, often we just use 1 layer because we don't really care that much about saturated groundwater flow on the order of like a week or 2, right? It's just not important. For each layer, you have to enter the initial discharge, the fraction, the linear reservoir coefficient, so that's the R from that equation a couple slides ago, and then the number of reservoirs. I'll talk to you about all of these. The fractions are used to emphasize or de-emphasize layers, right? So if you have 2 layers, you basically apportion the amount of volume that enters each layer. Those fractions do not have to sum to 1, but they can't sum to anything greater than 1. If they sum, let's say you have fractions for groundwater layer 1 of 0.4 and then 0.4 for groundwater layer 2, that means 40% of my losses enter groundwater layer 1, 40% enter groundwater layer 2, and the remaining 20% is lost to the aquifer, right? It's percolated. It's actually lost from the system in HMS. This is a way of dealing with certain geologic formations. We don't have a groundwater model in HMS, but basically this is a way of dealing with too much volume in your system. Okay, we will talk through more parameters now. Like I said before, you can model interflow and groundwater flow, and the way that's typically done is that layer 1 is used to model that quicker responding interflow, and then layers 2 and maybe 3, you might have a total of 3 layers. The last 2 are typically used to model that saturated groundwater flow. And the way that you kind of differentiate is by applying different reservoir coefficients. Hopefully you can see this, but I have a groundwater 1 coefficient, which is 24 hours, which is shorter than my groundwater 2 coefficient, which is 80 hours, right? So the longer time means that you're holding that volume, right, staying in the ground for longer. Oh, I should also mention, so within each groundwater layer, right, so you can have 1, 2, or 3 layers. Within each layer, you can have multiple reservoirs, right? So the terminology is a little confusing. Linear reservoir Baseflow method, you can have 1, 2, or 3 layers. Typically 1 is used to model interflow, 2 and maybe 3 are used for saturated groundwater flow. But then within each layer, you can have multiple reservoirs. And the reason you might do this is to attenuate the water in those layers for longer. So for example, let's just say I have 1 groundwater layer. I'm only dealing with interflow, but within that layer, I have 2 reservoirs. What that does is I have, let's say, 2 reservoirs that have the same groundwater coefficient, let's say 24 hours. So the first reservoir has that R, the coefficient of 24 hours, and then the outflow gets passed to the second reservoir with the same coefficient of 24 hours, right? So you can see how that response is slower because of attenuation, and we have hydrographs to show that, right? So a lot of knobs to turn when you're using this method. A lot of this deals with timing of the response of the system. Again, if you're working in short scales like a week, you can look at some of these coefficient values, right? And a lot of this is going to happen outside your event window, right? So this is more important for continuous simulation or systems that really have a quicker responding interflow, maybe groundwater flow. All right, so let's talk more about our linear reservoir coefficients. Larger coefficients attenuate the Baseflow contribution. So let's look here, 6 hydrographs. The top 3, the largest, are the total flow, and then the bottom 3 are Baseflow. I think we only have 1 Baseflow layer here and only 1 reservoir, but we vary the coefficient of that linear reservoir. So the solid lines correspond to a groundwater 1 coefficient of 12 hours. The kind of longer dashes are 24 hours, and then the dots are 48 hours, right? So it doesn't really change the timing of the peak, right? Look at these lower 3 curves. The peak happens about the same time, but it does attenuate this timing on the receding limb, right? What we recommend for groundwater coefficients is that you initially set these as multipliers or multiples of the Clark storage coefficient, so R from that previous lecture. Okay, right? And the reason we do that is because you end up with a lot of parameters, right? When you have transform and you're using linear reservoir Baseflow, so setting it as multiples helps you kind of collapse the number of dimensions that you're working with, at least calibration-wise. It also relates the groundwater or the Baseflow response to your overland flow response, right? So that's useful for calibration purposes. You're gonna have to calibrate both your time of concentration, your storage coefficient, and then your groundwater coefficients anyway, so this is a useful starting point. All right, I talked about number of reservoirs before, but let's look at how that impacts the hydrograph. So again, within each layer, you can have multiple reservoirs. So here in the red box, I have 2 reservoirs for my groundwater 1 layer. In this case, the timing does get shifted, especially the timing of the peak, right? So again, solid lines, I have 1 step, dashed lines, I have 2 steps, and then kind of dotted lines, I have 3 steps, right? So you can see 3 steps, the timing of that peak is shifted by over a day, and then the attenuation is longer. So increasing the number of reservoirs will delay timing of peak base flow. So here we're looking at groundwater layer 2. And we're talking about that longer responding base flow or saturated groundwater flow. Top couple hydrographs are total flow. The smaller ones are base flow. You can see my groundwater 2 coefficient increases from 100 to 200 to 300 hours. There's barely any difference in the total flow hydrograph, right? Or sorry, the total flow hydrograph, yep, especially during the event. But this comes into play when you're simulating continuous simulations, you're modeling both dry periods as well as wet periods, right? So not a whole lot of difference when you're just looking at a couple of days, but this does become important as those simulation scales increase. Let's talk about groundwater fractions. These are really important. They can be varied from 0.1 to 1, and like I said before, the sum of all your fractions, so whether you have 1, 2, or 3 layers, that sum can be less than 1. It can't be greater than 1, right? You can't add volume in this method. If they sum to less than 1, then you lose the remaining volume to the deep aquifer, right? In HMS, it's lost. Like I said, this comes into play when you have too much volume. This is sometimes needed. So on the right here, I'm looking at my groundwater 1 fraction. I think I only have 1 groundwater layer in this, I have 2 in this case. But let's just talk about groundwater layer 1. The solid lines show a groundwater fraction of 1. Dashed lines, the fraction is 0.5, and then dotted lines, it's 0.1, right? So as I decrease my fraction, right, I'm de-emphasizing that groundwater layer. You can see that the peak base flow goes from about 4,000 to maybe 400 because of that change in fraction. Doesn't change the timing. This can also be used to emphasize one layer over the other. So maybe interflow is really dominant, in which case I would give my groundwater 1 layer a higher fraction than groundwater 2 and 3 if I had all 3 in the system. All right, initial discharge type, kind of like recession, you have a discharge per area and an absolute value of discharge. Just as before, we really recommend you use discharge per area. It's easier to apply over large areas. It's still really easy to estimate. You want to manually adjust this value based on an observed hydrograph. So you just plot up observed and simulated, and you take your initial observed flow divided by your upstream area, and that gets entered directly in HMS as your rate per area. So if you're in the US, it's typically CFS per mile squared. The last bullet point's important. You want to be strategic when starting your simulation date. Like I said before, if you're really smart about it, you can model only groundwater 2 and or 3, right? So if you're starting it during a dry period, like between any rainfall events, you can capture just the saturated groundwater flow, which makes it easier for you. You have fewer parameters to adjust, and you can set the groundwater 2 initial flow to, sorry, groundwater 1 initial flow to 0. And I'll just briefly mention, so the small 3 hydrographs here are just showing different initial discharge values. So the solid line's the smallest, it's 1 CFS per mile squared. The dashed is 5 CFS per mile squared. And then the dotted one is 10, right? So that impacts your initial value. All right, sum it up. A linear reservoir can be used for a continuous simulation. It can also be used for event-based simulation. It just typically collapses the number of parameters. If you're using linear reservoir for event-based, like I said before, you typically only need one groundwater layer. Not always the case, but a lot of the cases. And it can simulate both interflow and groundwater flow. What I want to highlight here is, what do you notice that's different about this simulated hydrograph, so the blue one, as compared to the one I showed at the end of the recession Baseflow? Does it better match the observed, especially in that second peak? Yeah, it better matches. So simulated hydrograph here better matches the observed, especially in that second peak, because of those two groundwater layers, right? We probably have more interflow in that first event, whereas the second event is probably more from groundwater 2 and or 3. And so by explicitly modeling those separately, we're able to better capture both recession parts of the hydrograph. But the question was, if the sum of the fractions for the groundwater layers sum to less than 1, is that a way of basically handling groundwater recharge in HMS? The answer is yes, right? Some of that volume doesn't show up in the channel, at least over the scales we're modeling. If you weren't simulating even just that lowest layer, what's called Baseflow here, the blue, right? You're going to be off by, you're already like taking out about 200 CF, maybe 150 CFS over that full simulation period. So from a volume perspective, that's significant, right? You would be dropping that hydrograph by about 150 CFS. In this case, we're showing that interflow is also a large component of this hydrograph. So if you weren't simulating either of those two components, the difference would be just your gray, the volume of just the gray versus the volume of the total, right? So it is still really important even on shorter scales, yeah.